Welcome to the Maine Science Podcast. I'm Kate Dickerson. Today's episode is a conversation I had with Matt Amalia, who wears quite a few different hats. Architect at Opal, co-founder of Timber HP by GeoLab, and he has one overriding theme: minimizing the carbon impact of buildings through design and new ways of building and insulating. Matt is focused on using Maine's institutional knowledge and legacy industries to create new industries and opportunities, all while changing how design is done from the beginning. I could have talked to Matt for hours, and I'm glad we were able to talk about so many different areas of his work in the time we did have. I hope you enjoy our conversation as much as I did. So Matt, welcome to the Maine Science Podcast. I'm delighted to have you here. You're our first architect, which always makes me happy for a bunch of reasons, because I think people forget how science-oriented architects are and this beautiful merger of science and art. But before we get into both architectural work and the other really cool thing you've got going on, I would love to know how you found your way to architecture and science and the art science meld of that.
Thank you for having me. I'm really excited to talk with you today and your listeners. For me, getting into architecture when I was younger, I really did like this idea of invention, like when I was really young, and sort of like coming up with novel ideas and machines and things like that. Kind of like very hands-on. But as I got older, I fell in love with kind of the arts and the visual arts and architecture itself as I started to understand more and more what that was. And, architecture, when you think of it, it's a really expansive career potential, because you're talking about everything, the interface of culture and community and nature and environment and individuals and living. And then you lay onto that materials and connection to nature and technical requirements for health and safety. And then actually, as I got further and further in sort of my design education and career, I really realized also then the impact that buildings have on the environment. Now, I hate to say it, but we haven't been doing a great job dialing in that impact. In architectural education, we talk a lot about design and aesthetics and materials and history and all of that. And we're taught that lines on the page become space. And that's a beautiful concept. For me, that was enough. I was so excited about three-dimensional space making. But the reality is every line on the paper is also energy. Every line on the paper is also carbon, a material, or resource. And so when you think about when we're designing buildings, when we're thinking about just the sort of fundamental problems we have to solve around creating space that are functional, health and safety, community engagement, all that, we also have to think about the environmental impact buildings have. And I think it's a pretty well-known statistic at this point that buildings account for about 40% of CO2 emissions annually. That's greater than any other sector, more than transportation. We talk a lot about electric cars, but buildings are just the absolute dog in the corner that need to be solved. And the problem is buildings last a long time. They're expensive to build. They're not easily updated, which makes challenge of buildings great. And I think in a way, unfortunately, I'm going to be a little critical here. I think the architectural profession and the engineering profession has sort of like shied away from that challenge. We really haven't taken that challenge head on, because you did in your intro. I love it. You said, like, architecture is this intersection of art and science, and it should be, and in many cases it is, but really the intersection of art and science is the intersection in my mind of art and data. And we architects have been really quite unengaged with the data side of this, because we can model the impact of buildings. We can model energy efficiency. We can optimize this, but about 90% of architects choose not to. And so when we're talking about this 40% impact that buildings have on the environment, and you talk about a profession and the role we're playing, we really do need to not only engage with the art and the sort of community side of what architecture implies, but we also need to engage with the data and the environmental impact, I think, more hands-on, and take that responsibility more seriously.
How much do you think the responsibility of architects also has to do with engineers and how they think about it as well? Because I think some people don't quite understand or get, and I get confused with it sometimes too, is like, where does the architecture part stop and the engineering take over? And would we be better served environmentally if there was more partnership from the get-go? Or maybe I even have that wrong. Maybe there is. It's really interesting, right? Because you're serving the same purpose to get this thing built, theoretically. But if you could answer that, that would be great.
Well, actually, you have cracked into an amazing insight, kind of one of the fundamentals of where the problem lies. So well done. And I appreciate you bringing that up. You're making my job easier today. So to begin with, architects are generalists. The profession is so vast. You can do the smallest little toilet design, there's bathrooms for ADA solutions, which are critical, or you can be doing airports or industrial design, also all critical to be done well. It all is all important and it's vast. And we also have to rely heavily on consultants and engineers for structural design, for engineering around mechanical systems and design. But to that point, I think there's a sort of interesting question of where it stops and starts those responsibilities, to kind of to the nature of your point. And when it comes to building emissions, for example, or the building energy consumption, it really has to do with the assumptions around the building envelope as that relates to the environment. And that is the amount of glass, the type of insulation, the amount of insulation, air sealing, and then the mechanical systems. So what happens is when an architect comes up with a design, in most cases, as 90% of the cases, they quickly take that design and put it over to the engineer. And they say, hey, you need to give me a mechanical system which is appropriate for this design. And the engineer says, no problem. The engineer's mindset is, I am going to make sure that no matter what, this building will be warm on the very coldest day. So they're going to design for what we call peak demand. And peak demand, if you equate it to thinking about cars and engines and like sort of the efficiency of cars, is kind of like designing for torque or horsepower. Because you're going to say, I want this car to go from 0 to 60 in 3 seconds. And so they're going to design an engine to do that. And so when you look at peak demand for a building performance, they're going to say, I want it to be negative 10 degrees and completely 70 degrees, no problem. Never have a callback, never have an issue. That's how big and how powerful the HVAC system is to overcome the load that it's presented with. Now, the problem with that is, as you can imagine, if you design a Prius to go 0 to 60 in 3 seconds, you would never have an efficient Prius because you would have a gigantic motor having to do that. And the whole thing would not work because it's optimized for that power. What we need to do is design buildings for the equivalent of miles per gallon, which is the annual average load, which is to say, on an annual basis, how much energy does this building use, kind of averaged out? And how can we optimize the efficiency, therefore bring that load down and really focus on getting a data loop or an energy model, which allows us to make decisions on this sort of average basis, what the heating demand is going to be, where we can optimize, the thickness of the walls and the R value of the walls and the type of glazing we're using. Because then we can sort of look at it on an average performance basis, to where we can really look at the impact of the building envelope and not just look at the extreme point with the climate. It's sizing two different things. They're sizing a mechanical system. We're sizing in a building shell and optimizing the efficiency of the building shell. And if you do that well, actually, your peak demand is going to drop way down. But think of it. The engineer is not connected at all to designing or specifying the R values of the walls. They're just saying, oh, I have an R19. The resulting mechanical system is X based on the coldest day of the year. As an architect, for me, if I want to average out all those loads and kind of come up with an average per square foot per year, I'm going to want to make sure that my walls are appropriately thick and saving that amount of energy, because I'm trying to balance a very different equation, which is how the building actually performs in normal circumstances. And that is where we derive the efficiency of buildings.
So what do you do with that idea, which makes a ton of sense? What do you do for those peak times of peak heat or peak cold? Is it, if you design the building shell itself, then maybe you're not at 70 degrees, which to me honestly seems really hot on a cold day? Do you design the building so that maybe it drops a little bit, but then you're not doing this huge energy fluctuation to get to that? Is that how it works?
And that's the next level of this. Again, you're just feeding me the softball. So thank you. Keep it up. Really, the question is, what is your design objective? What are you trying to solve for, which is what you're saying? And for us, it's sort of like our goal is with Passive House, which is kind of the energy standard that we designed to, which proposes the building needs 90% less energy for space heat. Our goal is not to have a mechanical system ultimately. So if you ask a mechanical engineer, what's your goal? It's like, I want to keep this rather poorly insulated house warm no matter what. My goal is to say, I want to get rid of the mechanical engineer. I don't mean that because they play a role in larger structures and so forth, but the goal is to significantly reduce the heating demand, so that actually passive houses derive not from passive solar, which kind of is a 70s concept of energy efficiency, but actually passive heating system, which means no heating system, which means each body, I'm the equivalent of 100 watts. You're the equivalent of 100 watts energy. All of us cooking, making cookies, boiling pasta, running your computer. Those passive loads are actually the heating system. So we're using passive heating approach and passive solar, of course, versus an active mechanical system. And that's what the mechanical system designers set up to do. And the architect, therefore, needs to take the reins back and say, no, I'm going for a house design concept that actually does not require active mechanical systems. I will say, however, important to this concept with a highly insulated building envelope, a well air sealed envelope, high performance windows, triple glazing in our climate. As you get down to sort of like DC and below, then double glazing is fine because of the climate temperatures. But key to that is ventilation throughout the building with heat recovery, which means you're supplying fresh air, you're extracting polluted air or ambient air. And what's interesting about the system is that cold supply air passes by and the energy exchanges between the sort of warm polluted air. And that's how you actually, in this case, with your ventilation system in a passive way as well, you increase that incoming air temperature or moderate or temper that incoming air temperature so that you can continually provide fresh air, but it comes in at a recovery rate of about 90%, which actually then gives you tempered exterior air, which continues to allow the building to be cool. And you don't have to have a big penalty for having fresh air added in, like say through an open window or cracks in the building envelope or just through a fan. So part of really the mechanical system of a high performance building is ventilation system with heat recovery, because then you're ensuring also not only is the building efficient, but it's also habitable, healthy indoor air. And you're sort of balancing that with this kind of very simple, but in a way also sophisticated, just ventilation system. That's really the key mechanical system for these high performance buildings.
So how soon after you finished your education in architecture did you figure out that you wanted to really focus on building sustainability from that perspective? Was it immediate? Was it while you were getting in school?
No, that's a great question. So for me, I worked out of school for about 10 years doing a lot of sort of higher end design, custom design, really fun projects. Like that's what I thought I wanted to do because, as I said, I got into it in love with design. But as I matured as an architect, I realized that the impact of my work was very different than impacts of other professions on the environment. Say a dentist, like me going to work every day, I'm having a big impact with the lines I'm drawing, the decisions I'm making. It's very different than a lot of other professions. And so that concept started to dawn on me and I really sort of engaged with that. So after about 10 years of practicing, I realized that it was time, for me to take a leap and run my own business and launch my own business. But I also realized that I wanted to take my sort of interests and expertise in design and focus on high quality, beautiful buildings and take that, but also then combine it with the most high performance buildings possible. So after about 10 years, and this is about 2008, 2009, coincidentally, we had a massive housing recession. So it was a good time to think of something new because what else are you going to do? But for me, I saw it as an opportunity because this overheated market and just buying and selling and building the cheapest whatevers, that was no solution at all. I think collectively we came to some extent to that realization as well as the subprime thing took out the entire housing market. And what we did then is I formed a design build company called Geologic with a partner, Alan Gibson, who is a contractor. And our goal was to make the most high performance building possible that we could imagine. And a lot of what was talked about in sustainability back then was kind of LEED certification was coming on. And that was very broad. It wasn't specific about kind of energy performance. So that was the standard was talked about. But for us, it's sort of that doesn't do enough around environment, climate. And the overlay is, you'll recall back then too, we had oil at $100, $110 a barrel. People were not able to heat their houses. And these Maine houses are largely poorly built. They're old, they're unimproved, and they're very expensive to operate. And that really impacts people's livelihoods and well-being and their financial well-being as well. And the reality is we're wait a minute, we should be able to think differently about how we're building these buildings to not just go to a sort of sustainability certification, but actually solve problems. Like there's a problem out there and we're importing oil to heat homes that people can't afford. Let's focus on how we can solve that with better building. And that's how we came across Passive House, which had been in the US not very long. Katrin Klingenberg kind of brought it over and built her first house and started to demonstrate that. And it was a very niche kind of thing. And we got super excited about this crazy concept that a building could be 90% more efficient. But we were like, how? I don't know why. Is it viable in the market? Who knows? Is it just a German standard that wouldn't import? Do you need to have like some strange construction system that is only available in Europe? We didn't know any of that, but we were like, it seems like the type we want to make. So let's just build one and see what happens. And that's what we did. We built the first certified passive house in Maine. It was the 12th in the United States. So it was very early days. We had no idea what we were doing. My background actually is I have a degree from a German university in architecture. I speak German, very comfortable with German culture. And part of what my career has been is kind of looking to Europe, which I would argue, particularly Germany, is about 20 years in advance of us from sustainability standpoint, right? And it's just really kind of to start to import ideas and concepts and products that they've been developing for 20 years that we haven't had our eye on, and bring them over and kind of import them and sort of try and, I don't know, domesticate them, if you will, and just make it a little bit more indigenous and available in this culture. And that was Passive House, the first thing we did. And what was required is we did have to import windows from Germany. So we just called up some vendors and say, hey, we want to import windows. And they're like, sure. I mean, I'm speaking German the whole time. So, they're like, oh, no problem. And we made an order. You can import a Volkswagen just as easy as import windows. It turns out they're about the same cost too. So we just started to bridge the Atlantic thing and with our supply chain, which significantly improved our chances of doing cost competitive, high performance buildings. And in 2008, that was the big transformation, the big leap, I guess. But for me, it wasn't such a big leap. It was just I was totally curious. Can we do this? It didn't seem like a risk. It just seemed like, if we can reduce operational energy or cost, it's not the future of green technology or sustainability. It's actually just the future of building. Because if you can build it cost competitive, every building should be built that way. But we didn't know if that was the case. So we had to prove all of that out. And does it work in this climate and so forth, which we were very excited about the results. And I built my architectural career on just building passive housing.
So one of the things I've heard about passive housing, besides the fact that it's really cool, is the upfront costs are not insignificant. So it can be out of reach for people who don't have a lot of money. And I think actually we are failing in creativity with loans and things like that. I actually think there should be a way to get a mortgage that takes that into account so that you don't have to pay a ton of upfront costs. You can get it built into your mortgage and then you're just slowly paying it off. But is recognizing that, if I have that correct, is that what led you to kind of think about the retrofitting part of what you're doing with the fiber insulation, which I'm going to ask you to talk about next? So do I have that correct, that there's that assumption and we haven't culturally or financial systems wise changed how we approach it so that it then does become self-limiting?
Yeah, it's such a great question. And I think there's a few layers to the answer here. Just to be straightforward, on a single family residence, the short answer is yes. A passive house is definitely going to have a price premium over standard construction. It's going to have all the benefits of operational savings, as you mentioned. It's going to have improved comfort. It's quiet. It's healthy, all these things, but it is more expensive. And for us, we've been able to whittle that down to around 6% from a first cost basis. So it's not massive, but that's through a lot of supply chain stuff. It's through a lot of optimization, construction. The first passive house you're going to do is going to be twice, I don't know how many times, it's a learning curve, right? You really have to optimize in your crews and so forth. But for us on residential, we're always at premium. And really the reason that is residential structures are shell dominated. And enclosed floor area, you just have a tremendous amount of shell. And that's where you have to add your increased costs. Mechanical systems in residential structures are simple. So you'll have this really small one, like a 2,000 square foot house is a passive house you can heat with a hairdryer. Basically, that's this 2,000 watt for your peak demand. This is going back to our RPM discussion, or torque discussion. Peak demand is 2,000. It solves all the problems. So your mechanical systems costs do shrink, which offsets some of the investment in the building envelope. But to be honest, the mechanical systems of a single family house are not complicated. They're mostly heat pumps at this point anyway, which is actually better aligned because of the efficiency of the building and reducing total cost. What it really does as well, if you're thinking of a trajectory of zero emissions, which when we're looking at kind of the legislation on a national level, that's definitely where we're headed, zero emissions and net zero buildings. But the first step is zero emissions, so all electric. Then net zero is to be able to produce the electricity demand on the roof on site. Like ultimately, to be perfectly honest, passive house isn't necessarily the goal. Zero emissions and net zero buildings has to be the goal. Passive house is the best first step to reaching that, always, because you're going to be able to reduce the mechanical system, the demand, and the size of the solar panel. So once you're like hitting the net zero goal, the increased cost of a passive house actually starts to pay for itself because you have 30%, 40%, 50% reduction in your solar array. It's going to make the math work pretty well. Again, that's not required at this point, but it is where things are going, right? This net zero target by 2050. So that's one thing. The other thing, though, is when we look at large scale buildings, institutional buildings, which we have gotten into because we're really excited about it. I can guarantee you we can build a passive house at the same first cost as a standard build. Same first cost. We've done it time and time again. And the reason for that is the amount of insulation and the complexity of the building envelope, because the ratio is totally different. It's not shell dominated. It's internal gain dominated. It's by all those occupant loads. Your shell, you don't have to bump up very much because you have all these internal gains. Your windows, you do have to do triple glazing. You don't want those losses. But when you do that, typically in these large buildings, you'll have perimeter heating at the windows to keep the buildings comfortable. With the double glaze, you have such extreme loss. And you have radiant cooling, the body to body contact. So that interior face of glass, if it's double glazed on a cold day, is going to be somewhere in 30 or 40. If you're getting condensation on your interior window, that's because the dew point is reached and it's freezing. So that means it's below 32 degrees. It's pretty easy. And a triple glazed window, that will be about 3 or 4 degrees off room temp. So if you're standing next to a glass wall, and it's wintertime and it's 0 degrees out there, you're going to have a 65 to 7 degree interior surface temperature on that glass. That's the sensation of cooling that you would feel, which would be very little, versus having that glass surface being maybe 32 or 33 degrees. If there's condensation and frost, then it is, right? Or it's usually around 40 or about 40 degrees, but that is a lot of body to body radiant cooling, right? So with a large building, a lot of ventilation loads either way. So having heat recovery is super important, but that cost increase is minimal. You don't have the envelope, so your cost increase around the envelope is you're 20% more versus 50% more in, say, residential, just because the internal loads, and your mechanical system, because you're reducing the perimeter loops and all the other complexity of the load generation, heating and cooling, is actually going to be significantly lower. As a matter of fact, you'll have a greater cooling peak demand than heating peak demand in an institutional building in Maine. And that just says you won't have losses. So you're just having to worry about air conditioning. It's a heat pump, so your air conditioning becomes your heating system. So essentially what you're doing is removing the entire heating system out of your building, and you're just putting the air conditioning side, which can do heating and cooling. So that's where that first cost competitive comes in. Most people don't know how to engineer it. Engineers don't know how to engineer it. So as an architect, we've really had to lean into consultants to educate them and make sure that when they're doing their energy models and trying to do their peak demand load, that they really take into account the system design concept that we have going on. It's amazing because we're talking about the same benefits of passive house, a 90% reduction in operating costs. Which institution doesn't want that? We work with College of the Atlantic. They've been really supportive and forward-looking around engaging with next generation sustainable technology, not only in the operation side, but also in the material choice side with renewable recyclable materials. And, it proves itself out. So to your original question, there's a cross premium. Residential, yes. Institutional, no, it's amazing. It really isn't. Doesn't need to be. But again, that's optimized, right? The industry isn't there. So I'm not going to claim, every passive house. No, that you will not see that, I can guarantee, because there's just that learning curve, whether it's the architect, the engineer, supply chain, which windows are you using? What are the costs of those? Like, that is still developing. And to a certain extent, we just have to be patient because it takes time.
All right. I want to circle back to two things. The first is the building, it's the highest source of carbon. Is that industrial or commercial versus residential? Is there a breakup there? Does one sector have a larger impact than others?
That's a great question. And I don't have good data around that. I do know that from a square footage basis, we actually build more residential per year than we do anything else. I mean, we just build a bunch of houses, over 1 million housing units a year. And I don't know how the carbon breaks down, and operationally as well, geographically as well. There's a lot of fine grain to that. I think for me, like I always see it as a regional question. Like we're in a cold climate. You got to focus on the envelope. You got to reduce those loads. In the South, it's a heating climate and humidity. So that's a lot more mechanical. So it's well air sealing, a lot of ventilation, heat recovery, latent load. So dehumidification, avoiding gains. So shading and that sort of thing. So, it kind of diversifies itself slightly based on where you are. And then, of course, we'll get to this, the materials you use to build the building, right?
Yeah, I was going to let that one go. I don't have you for hours here, Matt. The other question I wanted to go back to is why Germany? How did you end up there? I realize we're totally going back here, but I don't think you grew up there. So how'd you end up there for school and what was that about?
Like my mom was a travel agent when we were raised, and there's 3 boys, and we were raised in central Michigan. And she loved to travel, and we therefore kind of got the bug of loving to travel. And she's an interesting person. She's from kind of California and ended up in the Midwest. And I don't know if that's exactly the perfect fit for her, but it didn't matter because all she really cared about was traveling. And so we all got into that. And then by the time we all got to our senior year in high school, she kind of kicked us out and said, you need to see more than the Midwest. So for your senior year, you have to go somewhere in the world. And so my oldest brother went to Japan, and then the brother before me and myself, we both went to Germany on a scholarship. And we just kind of landed there and learned to speak German, engage with the culture, and then realized that there's just an entire way of doing things. What I really engaged with was there's this sort of long-term approach of building value and being kind of careful and thoughtful about how we develop infrastructure and buildings and how that can benefit society and the environment, and being a lot more mindful about material utilization and stuff like that. That just sunk into me. And so when I started my education back in the US and then decided it's good to know what the rules of the game are in the US, particularly professionally, like as an architect and so forth. But I really felt like I really want to incorporate more of that understanding of this kind of level of detail, quality planning, sustainability that I saw in Europe. So that's what drove me to go back and study and kind of get a deeper understanding of how that plays out. And then I've just been incorporating those ideas, that understanding, and just maybe it's a kind of a point of view, how you see the world, about being more thoughtful and sustainable with your practices and your actions. And I think that's kind of impacted me as well.
I've been lucky enough to go to Europe periodically, and Ireland is my place. And what I've always struck by is how young we are as a country when you go to Europe, right? It's just could not be more obvious. And I think there's real benefits in learning from the mistakes of people who, as societies, have been around for a whole lot longer than we have. And how do we kind of steal what we need so that we don't make some of the mistakes they made, right? I mean, I think there's something really dynamic about American culture, but I also think we are really, really young in comparison to a lot of these other places. So why not take advantage of what they've already figured out?
Yeah, totally. I love that concept. And I also think because it's a dynamic culture, it can be influenced, and ideas can be adopted. And while we haven't been focused on efficiency for a long time, and there's been this major transition that's going on, when you start to take some of these European concepts and you push them into our culture, suddenly when the awareness is there, the adoption is massive. The adoption of Passive House right now is a hockey stick curve. The millions of square feet being built is just incredible. The impact on building code conversations and the net zero conversation and sort of zero carbon targets, it is transformational. And it really is, because once we started to change our minds, particularly on a policy level, realizing there's these technologies or concepts, it can happen extremely quickly. The reverse is not true. The reverse in Germany is not true. You're not going to change things quickly there. Now, luckily, they were going in a good direction with the sustainability thing. They've had other issues, but that's what's kind of cool about the US is we do change the direction pretty quickly, for better or for worse. But in this case, I think we're really seeing some very cool improvements and progress being made.
So taking ideas from Germany leads right into Timber HP. Yeah, it was pretty great. I'm glad how that worked out. So if you don't mind touching on that a little bit.
Okay. So Timber HP is a company. It's a startup that myself and co-founder Josh Henry, who actually is a PhD chemist, we started back in 2015, 2016. And to your point, the idea was that we had seen an insulation product made in Europe for the last 20, 25 years, insulation that was made from wood, or wood fiber insulation. Actually, how the feedstock comes from the residuals from the lumber industry. So the waste stream from making round logs into square boards for softwood. And, the overlap of what I was doing professionally with Passive House was basically, as I've been talking about, I've been using about 3 times the amount of insulation as a standard built building. And the problem was the insulation products I was using to insulate these buildings, there's a lot of problems. There was non-renewable, non-recyclable, made directly from some cases from fossil fuels or oil, combustible issues, and not to mention the human health, like handling insulation. Nobody needs to tell you is itchy, scratchy, and annoying. If you take a piece of EPS foam and you cut it in a field, it looks like it just snowed out with all those plastic microbeads going everywhere. Like, we tried to get rid of coffee cups in the 80s or 70s or whatever, because apparently they're unhealthy, but then we're putting them all over our buildings and calling it sustainable. Like, that does not work, right? And so from a professional standpoint, I was like, Passive House is good. But what I really did was I traded one environmental problem for the other. Operational savings was traded for carbon footprint, and I didn't solve a problem. And that's where Josh and I came together. Josh is a materials chemist. We were working at a local not-for-profit and just talking about like how an architect and chemist could collaborate, like to your science thing. And Josh is like, I have no idea how you can help me. I'm like, no, there's all these real challenges. Trust me. And he didn't quite see it until one day he came into the conference room, and we'd been kind of talking about how we'd collaborate. And we had a piece of wood fiber insulation because we'd already started searching for alternatives. And he's like, what's this? I'm like, oh, it's this great insulating product. It's made from wood. It's recyclable. If you cut it, it's just sawdust, no itchy, scratchy. It's biodegradable, but it performs really well. Our value competitive, just a fabulous material. And he's like, well, problem solved, right? You guys are going to use that? I'm like, not really, because basically insulation on a good day is air, and importing German air to the United States and putting it around a building is a kind of a non-starter financially. So no, we're not, but it's not manufactured domestically. And, I'm just like, I have no idea why, but it's kind of a not really a realistic solution. And then Josh is, as a materials chemist, like, why? Like, I get it. Like, we can make this. So we went up to Maine and started reverse engineering with the guys up there in the advanced composites and structures. And they figured out that we could easily make it in Maine. We have the feedstock. We went over there then and started to talk to manufacturers. And I think there's one manufacturer in particular that took our call and invited us over to meet with him. And I think he didn't feel very threatened by the architect and the chemist duo. He's like, I don't know what these jokers are doing, but they're kind of amusing. They speak German, ironic, because Josh speaks German as well. They speak German and they seem nice enough. So we got to know them, got to know the process, got super excited about the product, or actually 3 products. And basically, the guy who owned the company is like, look, why don't you guys take all of our financial model and transpose it to the US? We'll give you all our information just to see if you guys can crack the nut on if it's viable to produce domestically. So this is 2015. That year, we had lost 6 paper mills, and our economy suffered $1.6 billion net loss annually because of the decline of paper, right? It just hits rural communities disproportionately. It hits loggers and, sawyers disproportionately. And this is a story that's been happening since the 80s, right? With the WTO. It's the offshoring of industry, and it's been the trend. And as a result, the wood prices in Maine, particularly the residual markets, the feedstock for what we would use, have dropped basically down to extremely low levels and have stayed there. And so when we looked at the model of wood fiber insulation produced domestically with our low wood costs and low energy costs, we realized we'd be completely cost competitive with any insulation product on the market and with the sustainability benefits. And so for us, it was like, we can do this at this cost. It is totally worth it because it is a better product, and people are also kind of more aware about human health and material utilization. And it can also support our Maine economy, particularly in the rural sectors and in lumber. And so we kind of naively jumped into this. The German guy actually sold us his factory because he actually was producing, he had big MDF facilities and medium density fiberboard. And he had just this one insulation factory that he was an early adopter, but wasn't scaling with the rest. And he had his other focus. So he's like, I'll sell you the factory. We then bought a paper mill in Madison, Maine, the former UPM mill, which closed in 2016, one of those mills that closed. And we kind of put the two together. It's sort of like the peanut butter and the chocolate. You put the wood fiber insulation in the paper manufacturing facility. And we built a financial team. We built an engineering team. Fortunately for us, the people who ran the Madison mill, the very talented staff, decided that this was important for their community. So they didn't really know much about Josh and I, but they're like, these guys can be successful. This will be a great benefit to the community. So they jumped in and they helped us. We got an incredible marketing team together. And it's all Maine people. It's all Maine folks coming together with just incredible depth of skill and understanding. It was a heavy, difficult project, but that's kind of what Maine can do, right? We come together and we get things done. And, it wasn't about the gains. It wasn't about the future. It was about having to solve real problems and working together to do that. And it's just an incredible story, but it's just our culture, right? What we have here that's special. Like, we can do difficult things. We can take on humongous challenges, and we can be successful because we just dig in and work through it. If anything, this company is really a story about Maine and like the abilities and the sort of determination of the people who live here. So we've been super fortunate. We're now at a point where we're operating. We're selling our first products, loose fill, which is kind of a blown-in replacement for cellulose. We're getting our bat lineup, which is bat is a press fit cavity, kind of a traditional stud cavity insulation. That's starting production now. And then we have a third product, a board product, exterior insulation, kind of a replacement for foam. And that'll be starting up in December. So it's a really exciting time for us. An incredibly heavy lift, but amazing team. In total, we'll be creating about 134 jobs in Madison, and we'll be taking this opportunity, and we're kind of looking to the West Coast for a second facility because so many of the challenges that you see on the West Coast, are repeated here in Maine. So there's kind of a good fit and a good opportunity.
I've been following this story since long before I met you. I love the repurposing. I love the fact that it relies on incredible Maine institutional knowledge and it's rethinking fiber. I remember years ago talking with Habib Dagher, and one of his pushes with offshore wind was, why would we rely so heavily on fossil fuels where all the money goes out of state, right? And has no benefit. And this is another perfect example of money stays in the state and has an end product that is totally made here that people see everywhere. What was it? Angus King, who said no fish should leave the state with their head on, right?
Exactly right. Yeah. We have incredible resources, and I think kind of next generation sustainable technology, like people talk a lot about the green wave will create jobs and opportunity. And people are like, all right, let's see it. And of course that's happened in solar to some extent, but this is kind of one of these core, good old fashioned legacy industries here in Maine where it does do exactly that. It's a huge financial opportunity because it's big at scale, and it has to be. You can't build a small wood fiber insulation factory. You can't do it. And that's when we were raising money, people are like, well, why don't you do a small one? I'm like, you take a tree, process that thing in some small facility and tell me how that goes. It doesn't happen. Like, it's industrial. And the thing is, we shouldn't be afraid of it. We should embrace it. We let it go. And what we let go with in the 80s with China joining the WTO and completely rebooting this sort of international industrial manufacturing and trade is we lost 30% of our jobs in the rural economy because of that in that industrial sector. But that losing the jobs, those are skilled. People think of factory workers, and that's an important part of it. But there's skills around planning and electrical, mechanical that make these things happen. You lose those skills, they're gone. And that's where we got desperately close with Madison, is that we came in 2019 and bought the mill that had been closed in 16. If we came in 10 years later, the folks that ran that mill, that institutional knowledge, that understanding, they would have been retired, gone. And the ability for us to take an old paper mill, which is just a hunk of metal, unless you have the know-how, it would have been so much more difficult, if not impossible. So really timing is so critical here. But I think that's the story, though, where we are in the U.S. right now is we have precedent now that this can be done. It can be done sustainably with a very good outcome with benefits to not only sort of being able to produce and a revenue generating business that creates value, but also for communities, jobs and longevity, around that. So I think we're turning a corner, and it's really based on next generation sustainable technology. And I am super excited about what that means.
So one quick question about the insulation, because I have a feeling some people are going to think, really, wood? If I remember correctly, it's non-flammable, right?
Yeah.
So how does that work? Let's just ease the concerns of the people who are listening to this, that you're not increasing your fire risk by using the material.
Exactly. So our chief marketing officer, Scott Loiselle, brilliant guy, he said right off the bat, kind of comes from way up in northern Maine. And he said, with wood fiber insulation, the first thing you got to answer is fire, bugs, and water. And once you answer fire, bugs, and water, then people will have an open mind to think about it. And he's totally right. So fire, we take boric acid, about 6% by weight, which is a natural salt. And we mix that in what we call the wet process after we refine the wood chips, and we add that to the fiber, coats it completely, and it provides a Class A fire protection to the loose fill in the back. And that's important because Class A means you can actually use it on very large structures as a non-combustible. And it's very effective in doing that. And it sort of slots right into all the ASTM standards around how that building material is tested and utilized. So really extremely flame resistant. It's the same kind of treatment, say, as cellulose insulation would have, but we're using about half as much of the boric acid because it's applied in the wet phase and not dry applied kind of, which gets quite dusty. The board product, which is the exterior application, that actually has a paraffin, which by 1% by weight gets injected in the wet phase as well, which encapsulates each fiber with a wax layer. And it's amazing. Like, we use the board product on job sites, and you leave it out in the rain, you leave it in a puddle, it is completely dimensionally stable. Like, water, when it hits it, just beads up and runs off like a duck's back. And that's because of this paraffin coating. Extremely durable. But the other cool thing about it is it's like Gore-Tex. It's windproof, it's waterproof, as I just mentioned, but it's also vapor permeable. So if you put it on the exterior sheathing of a building, it's an exterior insulation, moisture will migrate through a building envelope to the OSB layer. And if that layer of insulation is a plastic layer, it will get trapped there and it will accumulate and it'll cause mold and degradation. If it's our product, wood fiber insulation, it's like Gore-Tex. It allows that moisture to pass right through and breathe out to the other side. So it allows the building moisture just to move through the assembly. So it's like wearing a Gore-Tex jacket versus a rubber raincoat. We all know what that means. It's the same in a building. And so really, like, code is driving continuous exterior insulation. But the reality is we didn't have the right product until wood fiber insulation came along, because foams really were a liability in that location. And we used a lot in passive house. And I know from experience, it's not the right solution. And that's why for us, we were really excited about the board product, because it allows us to take conventional construction, just add additional thickness of insulation. We can make the wood fiber board up to 9¼ inches thick, which is a very cool concept, because what we're actually doing with that is I have another company, Opal Build, where we're panelizing that with CLT. So in prefabricated, pre-cut CNC panels. This kind of goes back to the original thing you said. When we introduce a new material like wood fiber insulation, particularly the board, which has kind of unique durability, it's very stable dimensionally. When you start to combine it with other new wood product technologies like CLT, you all of a sudden have these all wood composites that can be completely CNC cut. So we take our computer model and take all that data and cut that into the building envelope. In these processes, we're able to reduce labor down to around 5% of construction costs. And so you said, well, our passive house is like going to always have a premium. My goal right now is to absolutely remove that premium, but we have to do it through different technologies. And with the introduction of wood fiber insulation, we can actually look back to our construction side and our design to construction and realize, okay, now we can start to automate and reduce labor through this kind of CNC cutting with these next generation insulating materials with zero waste, because we can take all the offcuts and grind them up into more insulation and really start to crack the construction cost performance nut. And in our case, we're really focused on the housing problem. So how do we translate these next generation materials into actual housing solutions that are high performance and sustainable?
So CLT is cross-laminated timber, also known as mass timber, right?
Yep, exactly right.
Before we go, I'm going to let you answer the bug question as well for the insulation.
So the bug question, the boric acid, again, is a mold mildew inhibitor and also bug deterrent. So bugs don't like it and mold and mildew can't grow on it. So to your point, when they hear it, they're like, it seems susceptible. But then again, we make our entire building structures out of wood. And we're really talking about making sure that the way we treat these products and install these products, that it is equally as durable as the envelope. And I think that's the proof's in the pudding. And these are really kind of like, these materials perform very differently than you would expect. And that's why when I first saw that as an architect, I was like, oh, that's how it works. Oh yeah, I want this. This is really the solution, because it's renewable, recyclable, non-toxic, performance competitive, but durable and appropriate for our construction system. We build in wood. We need to have materials that don't trap moisture, but also, to your point, aren't susceptible to water or moisture or fire. And we can achieve that with these products.
And the cool part too is, because it sticks with how we already build, the learning curve isn't as vast as if it was a total change in construction.
That's totally right. That's a lot of what my experience of like going back to this German side of me was, these German technologies are great, but if we tried to like sell German insulation as this German product, it would fall flat on its face, because the way they think of construction, the systems and the build, that's not how we build. Attributing a lot of our success to our CMO and translating this European technology to an American way of how we think about building, how we install layers, how we handle materials. He's done a great job because we need to really think of it in the terms of what our culture is, where our traditions are, and find that bridge. And I think, again, as we talked about, like the culture can move quickly once we have these inputs. It's just, we have to put them in the right place at the right time to help make that transition happen. And I think this is going to be one of those products.
Well, Matt, I appreciate both your time today and all the work you're doing. Like I said, I've been a fan from afar for a long time. When you spoke at the festival, your talk was one of the ones where people have come up to me still and say, who is that guy again? I want to know what he's doing. I get that a lot for the 5-Minute Genius, but yours is like way at the top for that, which was really fun. I think because people know what buildings are. So thinking about it in a whole new way, I think they just got really excited by that. It's more immediate than learning about cool genetics or cells that you have to actually visualize in your head, as opposed to like, oh, I live in a building. Oh, that's cool. So I appreciate all that you've done. I love what you're doing for Maine. I think it's super inspiring. And I love the reuse and the reapplication of a traditional industry and kind of being inspired by what that brings. So thanks for all of that.
Well, you're quite welcome. It's been a pleasure to talk with you today.
Thanks for listening to the Maine Science Podcast. Make sure you never miss an episode by subscribing on your podcast platform of choice. And please leave a rating and review. It will help more people find us and help spread the word about some of the remarkable people doing science in Maine. The Maine Science Podcast is recorded at Discovery Studios at the Maine Discovery Museum in Bangor, Maine. The Maine Science Podcast is executive produced and hosted by me, Kate Dickerson, and edited and produced by Scott Loiselle. The Discover Maine theme was composed and performed by Nick Parker.